All right, so now section 10.2, comparing two means. So this is going to be a repeat very closely to what we did with the two proportions from section 10.1. It's just, instead of using the square root of PQ over N for the standard deviation of proportions, we're going to use the sigma over the square root of N. Instead of using Z's, we're going to use T procedures. Okay? So, first recall the sampling distribution of sample means for a population that has a mean and standard deviation of mu and sigma. Describe the sampling distribution. So, center. The mean of my sample means is going to be equal to the true population mean. Spread. The standard deviation of my sample means is going to be the standard deviation of my variable, population standard deviation of my variable, divided by the square root of my sample size. Shape. We hope it's going to be approximately normal. It seems ridiculous to say approximately normal, right, when we haven't checked the conditions to see if it's approximately normal. Well, it should feel just as wrong to say that this is true and this is true without checking those appropriate conditions. In order for all of these things to be true, those certain conditions for inference has to be met. Describe the assumptions and conditions. Okay, there we go. Now we're back getting sensible here. For this, we just need an SRS. As long as we have a simple random sample, then our sample means are an unbiased estimator of the population mean. Here, 10% condition. Pseudo-independence. As long as we have pseudo-independence, I can use this formula. And here, this is the normal large sample condition. Here, the original distribution needs to be normal, then you're good for any sample size. If you're not good here, then you got to look at the large sample. If your original distribution is not normal, then hopefully your sample is bigger than 30, then you're okay. If not, you might have some problems. The sampling distribution of the difference of sample means is developed in exactly the same way we developed the sampling distribution of the difference in sample proportions. I'm going to spend a little less time on this, just kind of go through it. So the mean, or the expected value of the difference in my sample means, is the difference in each of the means separately. And since the mean of my sample means is the true population mean, this is going to be just the true population mean. Again, sounds like I'm getting all complex and fancy. This is just common sense. If you're taking the difference in, if you got two populations and you're going to sample from them and calculate the sample mean, the difference in those sample means should be centered about the true difference in the population means. That's just common sense. Spread, if the two samples are independent, and if we pass the 10% condition, then the standard deviation of the difference in your sample means is just going to be the variances added together to take the square root. Again, combining random variables. So if we take this standard deviation formula and square it, we get sigma squared over n. So that's the variance of the first sample, plus that's the variance of the second sample. Add the variances to get the variance of this. Take the square root to get the standard deviation of that. So this is the formula. It's on your formula sheet. Okay? You don't have to memorize it. Shape, if the two sampling distributions are both normal and the samples are independent, then the difference in the sample means is also approximately normal. Okay. Conditions, both samples need to be random. Both samples need to pass the 10% condition. Both samples need to pass this normal large sample condition, and your two samples must be independent of each other. For checks, they're kind of the same as before. It's just this one is a different check. For proportions and means, it's a different check. But we've done this before. You just got to do it twice now. Potato chips. A potato chip manufacturer buys potatoes from two different suppliers, Riderwood Farms and Camberley Incorporated. The weights of potato from Riderwood Farms are approximately normal. So here's Riderwood Farms. So it's approximately normal with a mean, call that a R, of 175 and a standard deviation of 25. Then Camberley, also approximately normal, with a mean of Camberley of 180, a standard deviation of 30. So it looks like Camberleys are a little bit bigger, right? A little bit bigger and a little bit more spread out. Okay, whatever, right? When the shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes from each shipment and weigh them. Let X bar C minus X bar R be the difference in the sample weights of the potatoes from the two suppliers. Describe the sampling distribution of the difference in sample means. Center. The center is just going to, the mean of my X bar C minus X bar R is simply going to be the mean of C minus the mean of R, which would be 180 minus 175, which is 5 grams. That's the center. We should put center here. We should, center. I don't think that would cost you points, but whatever, right? Spread. The standard deviation of the difference in my sample means, use the formula. Square root. Let's go back up here and just check this out. It's the standard deviation squared over the sample size, standard deviation squared over the sample size, square root all of it. So for Camberley, it's going to be 30 squared over, I think both of these sample sizes were 20. I didn't write that down, but 20 plus standard deviation squared over 20. Put that in my calculator. So there I put it in my calculator. Control Enter. 8.732. 8.73 grams. And I keep sounding like a broken record. I keep saying the same thing over and over again. That number is important. Why is it important? Well, or how do you interpret that number? Well, when I take sample means from each of these populations, right? And I take the difference in my sample means, these estimates, these differences in my sample means will typically be 8.7 grams away from the true difference in my population means, right? Whatever, that's what it means. Shape, probably approximately normal, right? Again, it's here where I always want to check the conditions, but did we check the conditions up here? We didn't check the conditions anywhere. Did it say to? No. Is it implied that we need to? I don't know. If this was a test question if this is a question on the AP test, I'd be a little bit nervous about not doing it. If it's my test, you can just not do it and argue it, and maybe I'll give you the points, but who knows? I guess this would be something you should ask during the test. Let's just verbally check the conditions. Centers, did we take random samples? Yeah, we took random samples, so that's okay. 10% condition. Do you think you think 30, not 30, you think 20 and 20, these sample sizes are less than 10% of all? I'm going to assume there's more than 200 potatoes. Okay. And does the sample from Riderwood, is that independent of the sample from Camberley? Yeah, I don't see why the sample I picked from Riderwood would have any influence over the sample from Camberley. So independent samples, so we're good. Normal. Sample sizes are small. So N equals 20, N C equals 20 equals NR. These are not bigger than 30. These are less than 30, so we got a problem. But both of these were approximately normal. So the normal part checks. You don't need big samples if your distributions are normal. So they all check out. Okay. Find the probability that the sample from Riderwood would have a higher average than the sample from Camberley. Okay. So all of this was looking at the distribution of x bar c minus x bar r. So let's make this look like x bar c minus r. So let's move that over there. X bar c minus x bar r. So I'm asking you to find the probability that your x bar c minus x bar r is less than 0. Well, again, we can find this as long as I know the center, and I do, and I know the spread, and I do, and I know the shape, and I do. So yeah, I can do this. I want to find the probability that the difference is less than 0. So this is 8. 8 puts me about to right there. So this would be about a -3. So that's going to be right around there, 0 or less. Normal CDF. Menu, statistics, distributions, normal CDF, lower bound -infinity to 0. Mean was 5, standard deviation was 9 point something. 8.73, 8.73, 8.73. Let's put out a guess. I'm going to go with 29%. Oh, I was going to say 28. 283. 0.283. Who needs a calculator, right? Again, same with this. We had a mirror problem like this for proportions. This is a very difficult probability question to answer if you try to approach it from a brute force point of view. But with sampling distributions, makes it manageable. We're doing some estimations here, but it makes it manageable. Okay? Let's go to the next video.